introduced to Professor Thomas Heine. So I had friendship with Thomas for many, many years, almost 20 years. So, and he was my host in my postdoc in Dresden. So Thomas was a professor first in Bremen, and later on he moved to Leipzig, and right now he returned to Dresden again. So he is an expert in 2D materials, and it's right now it's editor of 2D Materials and Application Journal. So everybody that is making 2D materials, MOS, and aromaticity knows the name of Thomas. So it's really a pleasure that Thomas gave the first lecture of this seminar, and thank you, Thomas, to accept this invitation.
Yeah, thank you, Gabriel. So, okay, it's my first talk for, I don't know, half a year, even more. So let me do that here. I have to share my screen. Okay. Okay, here we go. So the topic of today's talk is two-dimensional topological polymers, and that is a new topic for me for but more than a year, and I'm pretty excited about that. So what am I going to talk to you? So I will talk about functionality. Well, let me give the laser pointer. I would like to talk about functionality that is not coming from a functional group, but rather from the lattice topology, and by stacking. So most of the stuff that I'm going to talk about you can find in these three publications. Right? One of them is a Chemical Society review. It's from this year, authored together with Max Springer and Sayung Yu. So both are PhD students in my group. Agnieszka Kutz, who is also in my group. And the title is as the title of the talk. And the other one is News and Views in Nature Materials, so co-authored with Yu Jing, who is now professor in Nanjing in China. And that paper actually highlights that after our predictions, experimentalists could actually make these materials. And that was very, very nice. And in the second part of their time, I would like to talk about the proximity effect in crystalline framework materials, actually discussing yet another means to impose functionality, namely by stacking of two-dimensional layers. And that work is together with a group of Christoph Wöll from Karlsruhe, but otherwise from, let's say, similar crowd of people, Agnieszka and Max. Kamal Batra is a PhD student in my group, and Rosalba was doing some calculations many years back. She was actually coming from Gabriel's group, did the PhD in my group, and she's also included here. Okay, so that's more or less a plan. Let's see. So if you look up Wikipedia and you would like to know what is functionality in chemistry, you find the following definition. So it says, in chemistry, functionality is the presence of functional groups in a molecule. In organic chemistry and other fields of chemistry, functionality of a molecule has a decisive influence on its reactivity. And then you find here a lot of examples. In my opinion, that's a very stupid definition, right? So it doesn't say functionality is related to a function of something, of a molecule or of a material, but it rather tells you that there are some chemical groups present, and those may be able to provide a certain function. Okay, so it's not really a definition of something that we would like to see. It is a definition on something that provides a property, and that is a bit weird. So, okay, you might think, well, Wikipedia is not, let's say, the first resource where you should go. Let's go to IUPAC. And if you go to IUPAC, to the Gold Book, and you are looking for chemical functionality, you are first, or at least I was surprised, that there's no major entry on that. You only find a sub-entry in the subdiscipline in networks, right, in polymers. There's no main entry on chemical functionality. And even there, we have the same situation. right? Wikipedia has basically very good company. IUPAC only defines chemical functionality by the presence of groups, right? Of here, for example, the chemical functionality of a network formed by a Sol-Gil process from a precursor, such as whatever, is that of the vinyl group. Okay, so that's a bit weird. So what happens if a material does have a functionality, but doesn't have a functional group? And we have that. We had that for many, many years, for example, in surface catalysis. So for many years, people are working on surfaces and there were no functional groups available, yet there was functionality and people could do chemical reactions and drive catalysis. What adds a little bit of spice to that observation is the presence of topological catalysis. And I would like to draw your attention here to a paper authored by Claudia Felser and Sienna Rao that appeared in 2017. And to my knowledge, it's the first, or one of the first works where topological insulators were driving catalysis. Okay, so it's called Wild Semimetals as Hydrogen Evolution Catalysts, and it's a very nice paper. It got highlighted in Nature, and it's actually really interesting to read, and I think it really opens the door to something new. So we will come to topological insulators in a moment, that you understand what topology means, but I'm still in the introduction, and I would like to draw your attention that there are more materials like that. So we have just published very recently a paper in Materials Today Advances, where we have a material which is made out of palladium and bismuth, and topological effects make it very, very special. So there's no functional group. The functionality comes from the fact that we have a topological insulator. And in topological insulators, relativistic effects play something on the band structure. So what actually happens is that if you include spin-orbit coupling, and if you look here at this band structure, I will also talk about band structures in a second, you will get a very high density of states because you get this avoiding crossing of states. So this was very special, and so the catalytic activity of this material that we could actually calculate does not stem from the fact that we have here a topological insulator. It simply stems from the fact that the topology creates a very interesting electronic structure. So much to the start, right? So I would like to talk about functionality, but not the functionality that you're used to, the functionality that you are getting from functional groups. So I'm going to talk about okay, and the important thing is if we go to polymers, if we go to topological polymers, then we may go to metal-free 2D materials, and that means also metal-free catalysis and functionality by metal-free groups. So I will talk about two-dimensional topological insulators, the interaction between lattice structure and topological properties. I will talk about the manifold of two-dimensional polymers, two special ones, the Kagome lattice and the Leap lattice. I will show you what physicists do in order to investigate those effects that are first investigated in physics. And then I will tell you about the long journey towards highly crystalline conjugated topological two-dimensional polymers and give some perspectives. Good. So you all know graphene, right? And you all know graphene because it is kind of special, and the Nobel Prize was given, and it's two-dimensional, and it is very stable, etc., etc. But graphene is also the prototype two-dimensional topological polymer. So if you look at graphene, right, it has a lattice structure like a honey bee or a honeycomb lattice, like you can see it here. And if you want to describe this, you only need to describe two atoms. And you put these two atoms in a unit cell, and then you can calculate the band structure. And as we are here in a chemistry symposium, and this is very much material related, and I will give a lot of band structures, let me give a very, very brief crash course to those who don't know about band structures. Usually when we are in chemistry, we calculate energy levels, right? You have the HOMO, and you have the LUMO, and you have many, many other levels. If you would do that for a solid, you would get a very high density of these levels because you have many atoms in the solid. You have an infinite number of atoms. So instead, we are plotting the energy levels in a different way. We plot the energy levels, which you can see here on this axis, that's the energy axis, right? We plot the energy levels as a function of the momentum of the molecules, right? So this here is the momentum. So what direction are the electrons going? And the momentum, one can show that, I'm not going to do that here, is related to the position of in the reciprocal cell of the lattice. So we can take this lattice to a Fourier transform, what you do also in X-ray diffraction pattern, and then you get the reciprocal cell. Then you can plot this here. So this is done here. So you can see the reciprocal cell of graphene, which happens to be honeycomb again. You can see that here. Right, you have some high symmetry points, for example, this K point, and the other one that is essentially equivalent is K prime. And now you can calculate the energies. And what you would get is you have the occupied orbitals, which are the red guys here, right? You have the unoccupied orbitals, which would be the blue guys here. And now if you would follow along some high symmetry paths, for example, from here to here, that would refer to the traveling from K to M. And you can see the red path is a parabola. We can see that here in the band structure. The blue path would be a parabola. We can see that here in the band structure. In this way, let's say gamma to K would mean we would follow from the center of the Brion zone to the K point, etc. Okay, so this is the way we are drawing this. And if we draw that for graphene, people have observed a very special feature, and physicists got all excited about them, and that is a so-called Dirac point. So if we zoom in here, we can see this cone, okay? And this cone, at the center of this cone, you have just a point. And the particular part about this is if you calculate the effective mass of the electrons, that is given by the curvature of the band structure, we would have a kink here. And because of that, the electrons would have a zero effective mass, which of course is crazy because the electrons would then be able to be very, very fast. They are very fast, right? But not that fast. That can be then solved with the Dirac equation. And therefore, this point is also called the Dirac point. So far to a little excursion to band structures. So I hope that you at least have an idea now what it means when I'm talking about a band structure. So anyhow, what is important at the moment is that the properties of graphene are given by the lattice, not by the individual atoms. Okay, so if you are more, let's say, a synthetic chemist, you would say, okay, we are choosing the atoms in a way that we can create a suitable lattice, and then the lattice does have the property. But the point is, the property comes from the lattice. Now, what can we do with that? So there's another thing in graphene that is important, namely, it is a prototype two-dimensional topological insulator. And how can we show that? So if we calculate the band structure, what we have just done before, but we get this picture. I was just putting here the frontier band where you have here this Dirac cone. If you now include spin-orbit interactions, you realize that there's a very, very tiny band gap opening at the K point. So here, where we had a crossing of bands, where we got the Dirac cones, we open a gap. Okay, so there are no states next to the Fermi level. And this gap is very small. It's something like 30 to 50 microelectron volts, so it's very, very small, but it is there. And Heine and Mehle have first discussed this back in 2005. And that is one of the conditions that characterizes a topological insulator. And one can actually prove that these properties are there if we are going from the material towards a nanoribbon. And let me show this on the next slide. So we have here the nanoribbon, right? And I can show that here on the next slide. So if you take a nanoribbon like this one here, right, that's directly taken from Heine and Mehle's paper, then we open the gap, right? So this is very strongly exaggerated here. But we get here two states. And these two states, right, they must be there. They are protected by the bulk properties of graphene, right? Because we had these two states before, at the edges of the graphene, we must keep these two states. And that is a little bit complicated. If you are interested in that, go to topological insulators. People who are showing that, they always show you this picture here with a transforming coffee mug and donut, right? So they are topologically equivalent. And what is important for you is that this property, what you can see here, is stemming from the bulk and not from the structure of the edge. That means you can go and functionalize at the end. You can make it wider, you can make it smaller, you can make kind of something fuzzy over there. You will remain having here such a topological state. And that is very important because that actually means that this state is protected from the bulk. And whatever it can do, it will remain to be there. So that's very interesting if you think about a chemical reaction, because if now something happens here at the edge, it will not destroy our state here, okay? So that means if we are catalyzing here something, right, we still keep the same property, and that could be very interesting for chemical reactions. So if you would like to characterize it topologically, you want to write a paper about that, you have to do a little bit more. So you have to calculate something which is called the Berry curvature or the Chan number. But given the time that I'm having here, that I don't want to go into that. So we have a code that is based on PyTB, which is a free code. And you can learn everything about that in this Chemical Society review paper. It's a tutorial review that we just wrote this year. And there you can really look into that and learn about all the mathematical steps that are involved here. Good. So so far to the introduction, and so we have seen these Dirac points and these Dirac cones. There are other things that people are interested in, and these are so-called flat bands. Okay, and flat bands have been predicted by physicists for two different lattices, which are very famous there. One of them is called the Lieb lattice. Okay, the Lieb lattice is shown here. So the Lieb lattice says you have a square lattice, but then you steal some of the atoms. Okay, so looks like that. Okay, so you have these guys have 4 connections. This guy has only 2 connections, and you can make that in different ways, as shown over here. The other one, and that one is supposed to have flat bands according to calculations. The other one that is interesting is a Kagome lattice. And the Kagome lattice, if you look at that, it somewhat looks like a honeycomb. So if you would put an atom in the center of these green guys here, you would get exactly a honeycomb lattice. But now your atoms should be here on the white dots, right? And it looks a little bit different. So that's a so-called Kagome lattice. And both of them are supposed to have a flat band. And physicists were very excited about that. So they wanted to create these lattices. You don't find them in nature. You can go to the crystallography databases, you don't find these lattices. So physicists thought, okay, now, so you can see here this Lieb lattice and you can see this Kagome lattice. And in order to implement that, physicists thought, okay, we cannot do it with atoms, we cannot do it with other things, but we can do it with optics. So they were actually creating optical lattices. And if you're interested in that, you can actually go to these papers. There are 2 back-to-back physical review letters here from 2015. So here's another one in PRL, just in order to have an idea. They are playing with a lot of mirrors and a lot of lenses and so on. They can create these lattices here in a very optical way. And if they do that, they have to do that at very, very cool temperature. Therefore, I wrote here, this is therefore I wrote here, this is ultra cool physics. Then you can actually create a band structure, and this band structure has this flat band here, this black flat band. Okay, so people have done that, but not for electrons, only for photons. And photons are not fermions, so that means you cannot really play with, or you cannot really exploit the band structure. So they said, okay, they would like to have it for electrons. So what did they do? They did a real brute force approach, right? So they went for the electronic Lieb lattice. So what they did was they took a surface. In this case, it was a copper 111 surface. They took a STM, a scanning tunneling microscope, and they were placing individual carbon monoxide molecules at the positions where you would expect the Lieb lattice. And then they did a lot of stuff there, and they could prove the states. They could implement that, they could get the Lieb lattice, and they could actually prove the band structure. But that works at 5 Kelvin. And us being chemists, I think we can do much better than that. We can find better ways to create these structures. And if you want to do that, you may ask yourself first the question, okay, what structures could actually be interesting? So, and if you go through the databases, that you can find in 2 dimensions, you have something like 200 nets, but 11 of them are very simple. These are the so-called Kepler nets or vertex transitive nets. And before we are actually looking into them, right, they are more rich than just the Kagome that we have here and the Leap lattice, which is not member of these 11. The question would be, what would be their properties, right? What kind of properties could such structures offer? And that is a project of Max and Zayung, right, who are working on that. And in the very beginning, one can do something very simple. We can just implement a tight binding approach where these lattice sites are interacting, right? So all the white ones here, depending on the lattice, one can actually look into the properties. So a tight binding approach is very common in physics. In chemistry, we would call that a Huckel calculation, right? It's just that we have to include the translational symmetry of the lattice. Otherwise, it is nothing else than a Huckel calculation. So that means we have a carbon network, and we say, okay, we have a parameter that gives us the interaction of this carbon atom with that carbon atom. We will completely neglect the sigma framework here. And if we would like to have second neighbor interactions, we would take this T2 parameter here. And all this we can put then into a matrix, and we can actually look into that. So here's another picture showing that for a hexagonal lattice, so-called HXL, or for the honeycomb lattice. And in the same approach, we can also include spin-orbit interactions, which are given down here, right? And so that means we have all the physical interactions what we would expect in this lattice. So what would be the results? So if you have a regular lattice, you already know that for HCB, which stands for honeycomb, because there is nothing else in graphene. So if we have just the interaction, we get the Dirac cone. If we enter second order interactions, not much happens. If we include spin-orbit interactions, and we do that very, very strongly, we open a gap, right? And then we will get here a one-dimensional ribbon with the protected surface states. Okay, so we knew that, so our approach works. We can do the same thing for a hexagonal lattice, and what is the result? The result is that we always get a metal. Okay, that would be always a two-dimensional metal. We can go to a square lattice, and again, we would always get a two-dimensional metal. Okay, so we can then move on and try more lattices. So here I have some more examples. One of them is a Kagome one, where we have something like in graphene, right, the Dirac point, but on top of that we have a flat band. And such a flat band is quite interesting because that could actually cause superconductivity. And now if we are putting in spin-orbit coupling, again, we can open gaps here to open the Dirac point, or we can open the touching between the flat band and the other electrons here. And moreover, the flat band is not so flat any longer. Again, we can put the ribbon. And we can continue and have more and more of those. Okay, I don't want to go through everything. But what is now interesting is if we think about chemistry, that we are not having atoms that are interacting, but groups of atoms. Then we should think about the interactions. So for example, we could actually, so we have seen that if we are adding second neighbor interactions, we may slightly change the band structure. It didn't happen here. We can add spin-orbit interactions. We open some gaps, and then we can check the topological properties. And this one basically tells us, okay, the Kagome lattice is very topological. And we can do that with many others. So here we can see a lattice which is called FES, and that one is KRB. And if you're interested in that, go to our tutorial review and look into that. I think there's a lot of stuff that could be interesting. But now we were very, very abstract, and we have to come to chemistry. So let's think how we can build these nets without just using atoms. For example, let's build a supergraphene. So instead of having two carbon atoms here, let's take two molecules. And these two molecules are called heterotriangulines, right? And they can be found, they can be purchased, whatever. And you can see the structure, right? And that means our, so we can polymerize that and we get this structure. And that means our graphene is now made out of a polymer, okay? Now the question is, what would be the property of the electronic structure of this polymer? And there we go, okay? This is graphene, and this is our polymer. And you can see very easily, okay, that looks the same, right? That means we can now create the band structure of graphene with a polymer. And okay, you could say, well, take graphene in the first place. We should, because graphene is very easy, but maybe we would like to go to other networks where we don't find a natural product. So if we go now to molecules, we can express now many different connection points with different functional groups. Okay, so for example, we have a C6 unit or a C3 unit or a C4 unit, etc., etc. And we can implement all kinds of different networks. In fact, we can include all of them here. And that means if we have done that, we create essentially any of the lattice topologies, and that at room temperature. So that means we don't have to worry about some super clean surfaces and 5 Kelvin and so on. We can do that at a real temperature, and we can think about a real world application. We definitely can do that. How can we do that? So first, people tried that in silico. So here's an example from Jean-Luc Bredas and Will Dichter's group that has been published last year. So here people were thinking about the square lattice built by these porphyrin units here, or by these kind of units here. If you go through the literature, you find other stuff. And so he implemented the Lie lattice in silico. So that would be the band structure of the very abstract lattice. And that would be the band structure if you do it in such a molecular framework. Okay, so, but now we would like to work together with experiment. And how can we do that? And we were starting from covalent organic frameworks. So covalent organic frameworks are nothing else than stacked polymers. And I was having actually the privilege to work together with Rahul Banerjee in the very early times when covalent organic frameworks got actually popular. We shared some of the very first, very important works. Essentially, what I would like to show you with that transparency is today, many people make COFs, and these COFs are getting better and better in terms of crystallinity. In fact, a lot of chemical reactions have been developed, and these are not all of them, which can be utilized to polymerize these COFs. And to move on here, that's a joint work together with Matt Addicoat, who was postdoc in my group and who is now professor in Nottingham, Trent University, and Dongin Jiang, who was in Japan before, but he's now in Singapore at National University of Singapore. So this paper here contains something like 100 successful syntheses and something like 10,000 calculations. And essentially what we have shown here is that we can use different building blocks, which are either trivalent or have 4 connection points, like you can see here. We can use different linkers of different length. We can create regular lattices or lattices that are also geometrically distorted. So you get a little bit the idea what is the power of the synthetic approaches that we may have. So that was a big advancement. And if you want to have a look how that looks like atomistically, it looks a bit messy, but at the end of the day, this is just a molecular, regular framework with very high periodicity. Good. So that was all nice, but it didn't help us. Right? So, because what actually happened is that the typical covalent organic frameworks and also MOFs are not much more than regular assemblies of molecules. Essentially what happens is that the atoms between the centers, they don't interact very strongly. And that means that the properties of the network have very little, actually no impact on the materials property if you don't have a strong interaction between the individual molecules in the network. So that means we need to have the network topology such that the electrons of the individual molecules can talk together. With other words, we have to conjugate them. And there was a very big debate about who was suggesting or making the first fully conjugated framework. Actually, to settle this debate, The suggestion came actually from these guys in 1979. So it's very, very old. Roald Hoffmann and Woodward and so on. So they were suggesting that already in 1979. But the first ones that was really published, that was the paper with Dongyin Zhang in 2017. And at the same time, the group of Jinyang Fang was having a very similar paper. So here we get fully conjugated networks. That now means that in such COFs, we get a band structure. Good. So, but these are COFs. And in COFs, we have interlayer interactions, and the interlayer interactions will very strongly distort the properties of the network, of the two-dimensional network. We have to do something about it. We have to go to two-dimensional structures. This we can do.
Good. So in order to go to monolayer, we can use a couple of tricks. One of the tricks is that we are using the reaction only at a surface. So for example, on a gold surface. The second one is a Lamieux-Blodgett approach. That means you try to do the synthesis at the interface between liquid and air, or between two different liquids. And you can also catalyze it in order to make that a little bit faster. So here's a nice example by Miroslav, who was working together with Dieter Schlüter. So he wanted to polymerize these type of molecules, which have hydrophilic groups on that side and are hydrophobic there. You can put that on an interface, a pre-assemble, then you interact the polymerization using light, and then you get these films here. Okay, and this one here has been written by a laser pointer. I mean, just to give you the idea how this Lamieux-Blodgett synthesis works. But let me go back to the Kagome lattice. Kagome comes from a Japanese basket making thing, so you can see the lattice. So it looks very beautiful. And it's also related to the honeycomb lattice. So you can see in blue with gray inset the Kagome lattice, and in black the honeycomb lattice. And actually you had the idea to put molecules that are triangular, they're called triangulines, together to a network. And let me explain to you very quickly what actually happens. So these triangulines here, they are triangular, and you can put them together to form such a Kagome lattice, as shown here. So you can functionalize these molecules both at the rims and in the center. The rims are not so important for the moment. We can just have here these oxygen bridges. But in the center, we can actually change boron, nitrogen, and carbon. And of course, you know, boron has 3 electrons, carbon 4, nitrogen 5 to share in this area. So that means boron gives us an orbital, but no electron for the pi system. Carbon gives us an orbital and an electron. And nitrogen gives us an orbital and 2 electrons. And then you calculate the band structure. The band structure always looks the same. It contains the Dirac band that we know from the honeycomb lattice, and it contains flat bands that we know from the Kagome lattice. And now if we put borons inside in the network, then our Fermi level is here. So that means we are running out of electrons over here. That means the top band is flat. So this is still occupied. That one would be unoccupied. That means we would have a system where only the electrons would do a conductance, but the holes will not. If we put carbons, we will end up with something that is like graphene, if you want, call it supergraphene. And if you put nitrogens, you reverse the situation of the boron. That means now the highest occupied orbital is here. That means you would have highly mobile holes and very, very immobile electrons. So what I told you here was shown in this very schematic scheme. On the next slide, you can see we tried here many, many different triangulines. They are all available. You can all buy them. They all have different HOMO-LUMO gaps, so this is not really a big specialty. And even they have been polymerized before, what you can find in these 2 papers that are not from us. Okay, so that was done already in 2017. Okay, so so this I explained already. What I want to show you here is what I explained before, right? So if we look at that, this actual feature, you find this in the atomistic calculation. So this here is a sketch, and that is what you get out from DFT. On the left-hand side, you have the boron systems with 3 different functional groups, and they all show the same thing. You have a flat band, and then you have a Dirac. Okay, and that here we have different bridges, and then here, but they're all the same. Here have the carbons, and our Fermi level is in the middle of the Dirac in all 3 cases. And here we have the nitrogens, and we have the same situation as before in the sketch. So on the top of this Dirac band, we have now a Fermi level, right? And that happens for all 3 of them. So that means the idea that we can put the molecule and form the network works at least in the computer. So and here, again, we looked what happens if we are allowing the system to relax in a freestanding way. The answer is not much, so I don't want to discuss this here in view of the time. I would rather like to come to this point here when we are discussing about the flat bands. If you talk about flat bands, and you simply have dangling bonds. Okay, so and in this case, it's not the dangling bonds. Now I'm told that my internet stability is, so I put off my video for a moment. Okay, so I hope that everything is still okay then. Okay. Okay, so but this year we were invited by the editor of Nature Materials to write a highlight of experimental work where we just summarize what I told you here. So this kind of network out of this kagome is made out of a honeycomb and a kagome network. And if you put the 2 together, you get the band structure that I was just mentioning. And what actually happened was that this has been done in experiment. So people have used these trianguline molecules. They are very stable, so they could do a very high temperature synthesis. They could create very nice single crystals. And could they measure actually the electronic properties? Yes, they could, because otherwise that would not become a Nature Materials paper. So that was the work here of Gagliotti and Contini. And so if you are interested in that field, it's a very, very nice presentation, very nice paper in Nature Materials. So you could see the structure is calculated with DFT. Here you can see the STM picture, so you can see a very, very large network. You can see a diffraction image. Here they probed the individual molecules, and then here they could actually show that they have the Dirac point here, and they could also show that they have the flat bands. Okay, so that means we could show experimentally that everything that I was telling you before can be realized, and that is the status of the research that we have today. That I would like to summarize, right? So we have today we can actually crystallize two-dimensional polymers, and there are various methods to do so. Okay? They depend, they differ today still with their quality. The first one that has been shown experimentally is this honeycomb kagome structure, and that has been synthesized on a gold surface, and all the electronic structures have been confirmed with an excellent agreement between experiment and theory. That means now that the world knows that we can do these topological polymers. Now you can imagine what is going to happen. We have all these crystal structures. We have so many two-dimensional molecules around, flat molecules around, aromatic molecules around. We can assemble them to form essentially any crystal structure. So I would expect that there will be many, many, many more papers coming out in the next month and years where this is going to be covered. So if I would have had time, which I don't, I wanted to show you something about what happens if you stack these molecules, but I'm not going to do that. I would like to just go and jump to my final slide. So if you stack these molecules, you would actually change the properties, and that is also again interesting because you can do some functionality, but let's not dwell into that at the moment. Right? So let's rather conclude here. And yeah, so what do I want to conclude here? So we can build molecular framework materials, and they should offer physical phenomena that are inherent in these different lattices, and we can actually make any lattice that is mathematically possible. That actually means that we can also create topological insulators, and all the features that topological insulators offer, and they should be possible at room temperature because we can make that with advanced chemical methods. There are a couple of challenges. So for example, it would be very good to have stable radicolite monomers, or that we can do post-synthetic functionalization to obtain, let's say, freestanding electrons in these monomers. Defect density is an issue, crystallinity is an issue, but I think these are all issues that can be sorted out in the future. And I would like to thank here my long-term collaborators. I would like to thank those people who provide funding for these things. And yeah, if you're interested in that field and you would like to do a PhD or so on that, please send me an email, contact me. That is always interesting. And with that, I hope that my computer will survive the question session. So I will just get out of the PowerPoint, switch on the video, hope to get the chat. And yeah, and then we can continue with the questions if you have any.
Now we will begin our second talk of the day, which is given by Professor Grau-Crespo. Once again, the presentation will last about 30 to 40 minutes. Professor Grau-Crespo, I will let you know when 5 minutes are remaining. Professor Gabriel Merino, would you please make the introduction?
Of course. It's really a pleasure to have Ricardo in this session. So Ricardo is from Cuba, and he started his research activity in Cuba, and later on he moves for the postdoc to the University College in London, and finally he's associate professor of material theory in the Department of Chemistry in the University of Reading in UK. So his work is really exciting about his modeling of disorder in solids. And for the last 2 years, I am checking his work, and it's really exciting. So thank you, Ricardo, for accepting the invitation, and it's a really pleasure that you accepted.
Thank you very much, Jessica and Gabriel. Just a quick word in Spanish. Hola a toda la gente de la comunidad latinoamericana de físicos químicos. Es un placer estar con ustedes hoy aquí. Ahora voy a hablar en inglés porque hay gente que se han conectado desde otros sitios del mundo. Pero es muy bonito el esfuerzo que se está haciendo para traer y agrupar a la comunidad de latinos trabajando en estos temas. Muchas gracias, Gabriel, y muchas gracias, Jessica, por todo ese esfuerzo. Okay, back in English. So my talk today will be about modeling site disorder in solids. Just want to briefly introduce the institution where I come from. It's the University of Reading, for reasons that we Spanish speakers always find very difficult to understand. It's not pronounced reading, it's Reading. And we are west of London in the UK. We have a very leafy, beautiful campus here, and I invite all of you to come and visit when it's possible again to travel. This is a department, and this building where the chemistry department is was actually designed by this guy who has a story in the presentation that I want to do today, because it was Edward Guggenheim was the head of the Department of Chemistry in the University of Reading, and he developed a lot of the theory of site disorder and solid solutions, which parts of it I'm using now in my own research. This presentation will be a very personal and biased introduction to the topic of site disorder, and I will try to introduce concepts that you might find if you ever need to face the modeling of materials with site disorder, and I will then show you some of my own work in the topic, just as as examples of some of these concepts. But it's the presentation is a combination of introduction and results. So in my group at Reading, we in addition to site disorder, we are very interested in photocatalytic metal organic frameworks and surface science and catalysis with these collaborators, Georg Held and Troy Bennett, in thermoelectric materials in collaboration with experimental group of Professor Anthony Powell. By the way, there is a postdoc opening there, just a quick promotion if you get in touch if this is a topic that interests you. And the site disorder topic, which is what I'm going to talk about today in collaboration mainly with Dr. Saeed Hamad and quite a few others, which I will mention at the end. So this is the topic of today's talk. So I will present a very general introduction to the modeling of solid solutions. I will introduce the site occupancy disorder SOD method and code, and I will give you some example of applications to investigate cation distributions at the bulk and surfaces of materials. Then I want to show you some extensions of these ideas. For example, using grand canonical ensembles instead of canonical ensembles, taking the average over configurations to calculate effective NMR spectra of solid solutions. And also, I will discuss a few possible ways of speeding up energy evaluations. So when you're given the task of modeling a solid, and then you look it up in a crystallographic database, and you find a partial occupancies in some of the sites. If you are a starting PhD student, you'll see, now how can I do that? How can I enter that into my input file, into my DFT code in VASP or Quantum Espresso or whatever? How do I deal with these partial occupancies? I will present a general classification of the methods that people use to deal with partial occupancies. And first of all, in terms of the representation of the disorder itself, there are three big groups of methods that you can think of. And the first one is to define a structure with average ions in some way. So if you are mixing these ions that are white and with these ones which are red, A and B, you can define the kind of a pink ion, and then you treat your solid as with normal periodicity in there. Now each of the ions is an average of A and B, and you can apply the normal periodic boundary conditions that you would normally do. And there are many different approaches that use this kind of concept, but they don't work particularly well, as you can imagine, because the local structure around each of these ions is not what you would expect if you had A or B. And therefore, if you have a phenomenon that is sensitive to local structure, this is not going to take you very far. Solution energies are typically very wrong as well. So people tend to use a lot the supercell approach, where you define a large supercell of your solid and then create a random or a special quasi-random distribution of ions. And the concept of a special quasi-random, I don't have time to go into the details, but the idea here, which was developed by the group of Sunga quite a few years ago now, is to choose a distribution that is not exactly random, but it is well thought in such a way that it mimics the distribution in the actually disordered solid, in the well disordered solid. So the radial distribution function, say, between species, it is built to mimic what you would expect in the disordered solid. And therefore, with this method, you can have a reasonable representation of disorder. But of course, the distribution is static. You have only one distribution of ions. That doesn't change with temperature. And you do require a large cell in order to represent all the possible chemical environments that each atom will have. And there is a third group of this very general classification, a third group of approaches that consists of using a configurational ensemble where you have, say, many different cells, each of them with a particular configuration. And now you can make sure that you represent all the possible chemical environments within the ensemble. This is cheaper because you, in principle, don't need to use very large supercells. And this also can be parallelized very easily. And also you can then take into account temperature effects and so on, simply by statistical mechanics in the ensemble, because you can change the way in which each configuration appears in the ensemble. So given these three broad categories, you can create a matrix of all the possible methods. If you, in addition to the horizontal classification that I just mentioned there, add a classification based on the type of evaluation of energy that you do. So if you do the things from ab initio, from scratch, using quantum mechanics calculations, you can do each of the three methods that I mentioned before. So for example, the visual crystal approximation is a way of doing average ions using quantum mechanics. In the supercell method, you typically use a special quasi-random structure. But you can also evaluate your energies, for example, using force fields of interatomic potentials. And then the cold gulp, for example, has a beam field approach that is incorporated to represent average ions. Typically, you can have a supercell using random distributions and so on. However, if you use the ensemble, you tend to use what is called the model Hamiltonian, where the energy is just a function of site occupancies, and you don't have any information about actual coordinates of the ions or even less electrons. There is a case, however, to consider the situation where you do an ensemble, but instead of using just the model Hamiltonian, you do an explicit evaluation using quantum mechanics of all the configurations in the ensemble. And I would try to convince you that there is a reason for doing that, even when it will be, of course, much more expensive. Why do we want to do it? Well, first of all, some interactions are very difficult to parameterize in the cluster expansions. I didn't mention here, cluster expansions are the typical method that I used for to evaluate the energies of ensembles, yeah? Where, for example, you evaluate the energy based on how many pairs or triads of different kinds you have in a particular configuration. But not all interactions are easy to parameterize in such cluster expansion models. If you have, for example, long-range interactions, if you have changes in electronic configurations and so on, you often need to evaluate explicitly using quantum mechanics. But the main reason is that quantum mechanical methods, and to some extent force field methods as well, can provide not just the energies, but also other properties for each configuration. You can get local geometries, you can get cell parameters, or electronic structure spectra, and so on. And then you can define configurational averages for these properties as well, and not only thermodynamic properties. You can also, because you have the degrees of freedom in terms of coordinates, you can have direct access to the vibrational properties of the disordered solids. You can extend the simulation to the surface, because the surface is not just the absence of one coordination. Since there are important relaxation effects and so on that you will need to consider properly, and then cluster expansions wouldn't really work well for that. So let me briefly introduce the statistics of how do you work with a configurational ensemble. Apologies if you are already well familiar with this, but I think it could be useful for someone who is starting on this topic. So basically, if you have the energies of your configurations, we call this E sub m energies here, then you can calculate the probability associated with each of these energies in the configuration ensemble using this Boltzmann factor here. And Z is the partition function, where that guarantees that the sum of all the probability is 1. But as many of you know, the partition function is also a very important quantity in thermodynamics, and it gives you access to the free energy, in this case, the configurational free energy of the system. Yeah, and this configurational free energy allows you to then calculate many other things. So if you have the energy of the whole solid solution, which is taken as the average of the energies of the configurations, in the same way as for any other observable, you can calculate the average over the whole of the configurations. W here is the total number of configurations. So if you have the energy and you have the free energy, you can also obtain the entropy associated with the disorder, or the configurational entropy. And this configurational entropy can be very generally written as the sum of the probabilities multiplied by the logarithm of the probabilities. This is the basic formulation. I will extend it in a minute, but the configurational entropy is a measure of the degree of disorder in the system. So if you have a system where you have one configuration with a probability 1 and all the others probability 0, then the term PM logarithm of PM only has value 0, or either here or here, and therefore the configuration probability, the configuration entropy is 0. And the configuration entropy, of course, it will increase with temperature in the whole range of temperatures in the system. So let me introduce briefly how you would do it if you wanted to have vibrational or pressure effects introduced in the simulation. Well, in that case, you can demonstrate that it is sound theoretically to weight the configurations according to their vibrational free energies. And now GM is the vibrational free energy. That includes already a vibrational entropy SB there. And then when you calculate the partition function, and from there you calculate the Gibbs free energy, then you can obtain the enthalpy as a sum over all the enthalpies of the different configurations. And again, the entropy can be obtained from the difference between H and G. And in this case, the entropy has two contributions. One that is the vibrational contribution, which is the average of the vibrational entropies of all the configurations in the system, and a configurational entropy, which has the equation that we discussed before. Yeah. So you can distinguish two, like a limit cases here. One limit case, the one configuration is much lower in energy than the other, than all the others, compared to with KBT. And in that case, the vibrational entropy, of course, the vibrational entropy of that configuration, and the configurational entropy will be 0. Yeah. And in the other extreme, you have all the configurations very similar in energy and compared with KBT, and therefore the probability of each configuration is 1 over the number of configurations. And in that case, if you put that equation in the equation for the entropy, you get that the configurational entropy is KB, the logarithm of W. Yeah, the well-known equation. And this W is the combinatorial number of possibilities of n, lowercase n in capital N sites. Yeah, capital N is the number of sites, and in the limit of a very large supercell, in the limit of the infinite supercell, you can demonstrate that the configurational entropy given by this equation here converts to this equation that depends only on x. Yeah. This is a very useful equation, and you will see some examples of applications now. But it is worth remembering that it's only strictly valid in the limit of full disorder. Yeah. So if you are doing thermodynamics in a system that has partial disorder, you need to consider doing the full formulation. The general equation for the entropy like this is the one that should be used in intermediate disorder situations. You need to apply some corrections for supercell size, as those described in the paper that I cited below. But anyway, I don't think that the main purpose of what I am talking about today is to calculate thermodynamics. If you really want to calculate thermodynamics, the best way to do it is to do cluster expansions in very large supercells and so on. What we want to do here is to calculate other properties beyond thermodynamics. The problem of this exhaustive approach to enumerate all the possible configurations is, of course, that the number of configurations grows very quickly, If you have, for example, 3 substitutions in 12 sites, that generates 220 configurations. If you're doing calculations at DFT level, the number explodes too quickly to do anything useful. So you need really to do something else. You can do random sampling. You can try to incorporate some calls to your DFT program using some important sampling algorithm like a Monte Carlo or something like that. And sometimes you can, not always, and sometimes you can reduce significantly the number of configurations by taking advantage of the symmetry of the crystal, sometimes by 2 orders of magnitude or so on. The idea here is that you only need to calculate the inequivalent configurations. So if you know now the degeneracy of the configuration, which is the number of times that each configuration appears in the whole configurational space, the probability has to be multiplied by that degeneracy. And these configurations are found because the equivalent configurations are always related by an isometric transformation in the lattice. Yeah. So if you realize that all the isometric transformations in the lattice are contained in the symmetric group of the parent structure, including all the superset translations, then you can easily figure out what the different ones are. And so for example, if you have a supercell symmetry like this, then a mirror symmetry in the unit cell is also valid in the whole supercell. And then you can figure out also that there are also translations, of course, a translation symmetry. So if you have a defined configuration like this, and there is a mirror symmetry, you don't need to calculate this one and this one. They are both identical, yeah, and they are identical to all the translations of this one. So these 2 configurations are the same. So you don't need to consider all of them. So this was incorporated in this code, the SOD, which has a few features there to, for example, given the crystal structure and the effects that you want to calculate. So the substitutions, it generates input files and then does some post-processing and obtain thermodynamic and other properties that you want to calculate. The source code is free to download. I have to say that there are other codes now with similar features. I think SOD was the first one that could do that, but now there are very nice codes that have been written recently. They are faster at generating configurations. SOD can be a bit slow, although to be honest, the computational cost of generating the configurations is relatively insignificant with the cost of evaluating all of them afterwards. But still, I mean, do have a look at other codes that there are. These are some examples of studies that have been done, mainly of energy materials using the SOD code, in catalysis as well, in minerals. I will skip this. So I have this here. I think I won't go into the details of how the SOD code works because there is a limited time. But basically, it is actually very simple to use. If you give it a go and you have any questions, feel free to contact me. I will skip these few slides here and we'll go straight to the applications. So the first example that I want to show here is a Shandite system where it has this structure and it has a disorder in the sites, in the second cation site of between indium and 10. And I just want to show you how with these methods you can explore the disorder and how you can calculate, for example, lattice parameters and site occupancies. The reason we are investigating this material is because of it has potential thermoelectric behavior, and it has a metal to insulator transition as a function of composition. And it is well known that the semiconductor state at 50% of doping it doesn't happen at any cation distribution. You need to have a particular cation distribution to get the semiconducting state. So there was a lot of interest from my experimental colleagues to figure out the issues of cation disorder here. And then we have done simulations on this. You can see all the details of the thermoelectric behavior and so on in this paper in Chemistry of Materials. But just to give you an example of how the cell parameters are calculated with SOT and how they are measured in experiments using Neutron diffraction. This is a very non-linear behavior in the cell parameters. This is not something that you could obtain with the cluster expansion very easily. You have to calculate explicitly the configurations and the relaxations to obtain this this non-linear behavior. And you see that it's a very good agreement with Neutron diffraction. And this is the disorder. This is the occupancy of the fraction of indium occupying either the M1 or the M2 sites in the solid. And the red line is what we predicted with the DFT plus SOT, and the dots are what is obtained with very expensive Neutron diffraction experiments. So it is actually quite nice that we can give a very good prediction of site occupancy and variation of cell parameters in the solid. The second example I want to show you is about calculating distribution at surfaces, which again is something that for which you need to do explicit calculations you cannot do with the cluster expansion. The interest in this system is a serious zirconia solid solution, and it has issues of possible phase separation at high temperatures. So you are interested in seeing how stable the distribution is. So this is the calculation of the enthalpy of mixing, which is the enthalpy of forming the solid solution from the pure phases. And we realized from our calculations that it is a very endothermic process, the mixing. That's a reasonable agreement with experiments, and we could predict also the solubility limits of zirconium in Syria. But this is secondary. What I want to show you is that you can also calculate distribution profiles of the ions at the surface. For example, if you take a slab given the 1-1 surface on one side, and then you calculate distributions here, then you can obtain what is the average occupancy of zirconium at different layers at different distances from the surface. And you can see that the surface, for example, in this material is depleted of zirconium in compared with the overall composition, that is the dotted line. This has, of course, implications for the catalytic behavior of these materials that we discussed in the paper that is cited below. I want then now to show you an extension of this idea today to use grand canonical ensembles instead of canonical ones. One of the first lessons that you learn when you start doing computational chemistry is that you shouldn't mix energies. You couldn't compare energies of systems that have different compositions. You wouldn't dare to do that. Your professor would tell you off. But there is a very important trick to learn, which is using chemical potentials. And with chemical potentials, you can always compare things that have different compositions, because you say, okay, whatever is not in the system, it is somewhere else with a chemical potential mu, and then I introduce it as a variable. And that allows you to couple calculations that you do in a solid, for example, with an external phase. So the idea here is, can we mix configurations with different compositions? And you can calculate the probability using, instead of the energy, you can have to calculate the energy minus n times the chemical potential, where n is the number of substitutions, and mu is the difference in chemical potentials between the two species that you are replacing. Yeah, and the value of mu has a direct connection with the fraction of substitutions that you have in the real system. Yeah, so you can either have, for example, know the fraction of substitutions, and from there determine mu, given this equation, because the probabilities depend on mu, or you can do the other way around. You can have mu, and from there get the fraction of substitutions. So the first case, for example, you can see this paper where we looked at orientational disorder in organic molecular crystals. The opposite is more interesting when you want to couple what happens outside the solid with what is happening inside the solid. For example, if you have hydrogen vacancies in a metal hydride, and that is in equilibrium with a hydrogen in gas phase. Yeah, this is what I want to show you in the next example. The magnesium hydride is a very important hydride with great potential for hydrogen storage. And one of the big questions and mysteries is why, however, it doesn't work very well. And the reason doesn't work very well seems to be that the dynamics of the hydrogen diffusion in magnesium hydride is very slow. So when you have your particle of magnesium and you try to put hydrogen in there, you form a layer of magnesium hydride around magnesium, and now hydrogen has to diffuse through that layer in order to keep hydrogenating more of the magnesium. The diffusion barriers for inside magnesium hydrides are not high. They are in the order of 0.2, less than 0.5 EVs compared to other systems with similar vacancy mediated barriers. There seems to be very little diffusion. So we wonder why that was the case. Maybe the reason is that there are very few vacancies in magnesium hydride in the first place. It's very difficult to create vacancies. So how can we estimate, given the particular hydrogen partial pressure, how many vacancies you have in the system? Yeah. So for that, well, you can take a configurational ensemble now that is grand canonical. So you have very different numbers of vacancies. We try different supercells here, presenting the result with a relatively small supercell. And now different number of vacancies in the system. Know that you can calculate the vacancy formation energies for mono vacancies and the vacancies and so on in there, and calculate the spectra. Now, when you apply the grand canonical formulation here, you can then relate the chemical potential to the partial pressure of hydrogen that you have in the gas phase. And then you link that to the probabilities, and that will give you what fraction of vacancies you can expect at any partial pressure of hydrogen outside. Yeah, and if you do that, you can build the absorption isotherms. Now, this is equivalent to say that instead of considering a very large cell with only with very few vacancies in the system, because the concentrations of vacancies are very small, we are considering a grand canonical ensemble where some of the cells don't have any vacancies at all, some of them have one, some of them have two. And in that way, we can treat any concentration that we want. That is the advantage of the grand canonical formulation. With that, you can build the pressure composition isotherms. And of course, one of the first thing that we notice is that yes, the beta phase that you see here is the magnesium hydride, and this is the number of vacancies that you can accommodate. If you have high pressures of hydrogen, then you can have more and more vacancies. But at low pressures of hydrogen, at some point, this simply transforms into a mixture of the metal and the magnesium hydride here. So it cannot accommodate a large number of vacancies, as you can see here, before transforming to the alpha phase. So the conclusion is that the very low concentration of vacancies in the system, which explains why vacancies are not really helping the diffusion kinetics in there. And the final example that I want to show you, I am almost at the end of I think one or two more, is the NMR spectra of solid solutions. So how you can take the average of the NMR spectra of the different configurations to create an effective NMR spectra and help you identify the local ordering in a solid solution. So we have been in collaboration with a group of Professor Sharon Ashbrook in St Andrews here in the UK, investigating the pyrochlores A2B207 because they have a lot of interesting applications, and you can tune their properties by doing composition engineering. So we really want to understand where the atoms go in these pyrochlores. And so we have been looking in particular at titanium tin pyrochlore in the B site with yttrium in the A site. And we have done a bit of thermodynamics. I mean, I say that the thermodynamics is not my main focus, but let me show you some of the of the approximations that we often have to take in order to calculate thermodynamics. So we calculated the enthalpy of mixing directly from the calculations in DFT. The PV terms in the enthalpy can normally be ignored. They are very small unless you are working at high pressures. And then in this system, for example, is a typical approximation that is used in mineralogy as well. You take the enthalpy in the limit of the full disorder, and then these enthalpies of mixing, which is the enthalpy, as I said before, in comparison with the equal amounts of the pure phases, you fit that using a Guggenheim polynomial. This is the guy that I mentioned in my very first slide, who was our head of department a few years, many years ago now. And Guggenheim devised these polynomials to fit mixing properties, which are very useful to create analytical expressions for which you can then calculate then free energies. And in the assumption of a typical ideal disorder here, then you can calculate free energies. And once you obtain free energies, for example, at 500 Kelvin here, you have a region which is like this here, that has 2 minima. And in the region between the 2 minima, well, not exactly between the 2 minima, but in the region in which the tangent, the second line here, is lower in energy than the actual free energy, that is a miscibility gap. This is a region where the system would prefer to separate into 2 different phases rather than form a solid solution. So you can calculate miscibility or estimate miscibility gaps for the solids. Now, more interesting than the thermodynamics is what happens with the NMR spectra. It is difficult to rationalize the NMR spectra based only on the different coordination environments that the yttrium central ion has. We painfully look at all the possibilities of the different chemical environments that they could have. But you can see here that depending on the number of things that you have around the yttrium, these are all the possible environments here. Depending on the number of things that you have around the yttriums, you have a range of possible chemical shifts in the NMR. And but there is not really a correlation. There is a too wide a range, which means that it's not just the immediate chemical environments. It's you have to go through the whole configuration to figure out what are the how a particular configuration generates a given chemical shift. So you have to do it with a full ensemble, and if you calculate the intensity of you calculate the spectrum for a given configuration, then you can calculate the spectrum for the whole of the solid solution by simply taking the average over the spectrum. And this is a spectrum generated purely ab initio without no experimental input at all, and this is experimental one. Then we can use the calculations to assign each of the peaks in the experiment and understand what the chemical environment is in each case. It was published in JACS last year. I am at the end of this, so I am not going to talk about this. But if you're interested in NMR and disorder, there is this work that I did with Professor Howard Colquhoun at Dresden as well, where we looked at the fractal NMR spectra in polymers, and that is related to the disorder as well. I invite you to have a look at that paper. I think I am receiving a sign that I should be concluding this soon. Just a couple of slides of one recent development, which is how to speed up the evaluation of energies in the system. The SOT code incorporates now, has implemented a way in which we can calculate, for example, 0, 1, and 2 substitutions, and from there very quickly extrapolate to higher concentrations. And that is that comes at no cost. So we can do really very quick calculations of many energies in the configurational spectrum. And it's similar to a pairs-only cluster expansions, but there is no fitting involved. It is just one command in the SOT code. It really does the job very efficiently. And we have been using that to calculate solid solutions in these beautiful metal organic frameworks. I don't have time to talk about this now, but let me just show you the results. So the calculations using the DFT method versus the calculation uses the simple pair-based extrapolation are very well correlated for high concentration. So we don't need really to do all the DFT calculations. You can even create some rescaling of that in such a way that you calculate one or two of these in the spectrum at DFT level, and then use that to rescale that and get a practically perfect agreement. This is the y = x line, yeah, between these calculations which cost nothing and this one which cost a lot of computing resources to obtain. So this is all in the new SOT version. This is my final slide with some conclusions and tips. So you can use SOT to calculate, to have a look at the distribution of ions in a solid solution. I wouldn't recommend to use it for accurate thermodynamics. For that, you have to use a cluster expansions or something like that. But from the configuration spectrum that you get in SOT, you can do many things, as I have shown in these presentations. You can sometimes what you need to do is to choose a representative configuration and shoot that wisely. If you have a lot of order in the system, of course, the lowest energy one is a good one. If you have a lot of disorder, then generate the SQS. You can do that with SOT as well, using gulp and SOT together. But bear in mind that that calculating all the configurations in the ensemble using DFT is not just to calculate thermodynamics. You have access to much more. You can average anything, cell parameters, you can calculate surface effects, you can calculate effective spectra, and so on. Remember the trick of using chemical potentials. Use that when required. For example, if you want to connect your calculations in the solid with an external environment, and use this SPV approach to extrapolate energies from low to high concentrations. So that's my final slide. I just finally want to say thank you to all the people who have collaborated with me on this project, and thank you all for your attention.
Expert in graphene, so actually it's one of the most cited person about this topic in Mexico. And it's the topic about magnetism and graphene is really exciting. So Romeo was our boss some years ago, and actually he extended the part of the theory in the department. So thank you, Romeo, for accepting this invitation, and I hope that you can enjoy the experience.
Many thanks, Gabriel. And I first of all to acknowledge to the organizers of this nice symposium for inviting me. And secondly, I apologize because some of my slides are in Spanish, because at the beginning I was expecting that the talk was in Spanish, but now I am switched to English. So I start. In this talk we are presenting results of first principles calculation study about the SP impurities in graphene, and some of them induce magnetism, and we are very interested to understand how this process occurs. And secondly, let me mention my collaborators are in this part of the slide, the names. All of them are working in this topic, but in different systems. So I appreciate this collaboration. So as is very common, this this kind of talks about graphene start with a mention of the people from Manchester producing and especially characterizing the spectacular or exotic properties of graphene, as we know, and the guy and Konstantin Novoselov report by first time in 2004, 2005, the first transport measurements and in general electronic properties of graphene. And after that, of all all these studies, they received the Nobel Prize in 2010. And one of these more interesting features of graphene is the electronic structure, because many of these anomalous or spectacular properties come from the linear relation in the band structure. In this plot, in the left, we are presenting the electronic band structure of graphene. It's very well known, however, it's interesting to emphasize some aspects. For example, in this part on the Fermi level, we find this behavior of the electronic band structure and the very small energies range up and down of the Fermi level. We can approach this band structure to a linear relation. The slope of this line is the Fermi velocity of the charge carriers in graphene, and this linear behavior in the energy produce many of these different properties of graphene, different with respect to their normal materials. One interesting point about this Fermi velocity is that this value is not exactly symmetric with respect to the holes and electrons. We can see the experimental values of the effective mass, determined by the Novosel group, and in solid line are or calculation at the beginning of this edge, graphene edge. So, in summary, graphene is more than a new material. For this reason, the linear behavior producing the Dirac cones, and the main feature was characterized as the Dirac fermions, massless Dirac fermions, or Dirac fermions with mass equal to 0, producing this kind of behavior. In particular, one very exciting property is the Klein tunneling, but today we are not talking about. So, after the discovery of these properties of graphene, we start a new era in the material science. We start the interest and the discovery of new two-dimensional materials. In this review, in 2016, was analyzed all these kind of new two-dimensional materials. As we can see, currently we have a very large family of two-dimensional materials with very different electronic properties, electronic character, going from the graphene, which is a semi-metal, to the insulator as the boron nitride. And in the middle, we have metals, superconductors, and semiconductors. So, but what about the magnetism in two-dimensional material? From many years ago, there exists a very interesting research in many places to try to find magnetic two-dimensional materials with intrinsic magnetic properties. And currently, we know a family of two-dimensional materials presenting intrinsic magnetism. This kind of system started more or less in 2016, 17, in the last 3 years, to appear this kind of materials. One interesting thing is that the first reports of this kind of materials was more or less complex materials, but in the last year, we can see this very simple structure with 3 atomic layers. In this case, the vanadium selenide 2, and we have intrinsic magnetic properties. One aspect of this, a common aspect of this material is that all of them contain transition metals or d electrons at the Fermi level. But one question that we try to answer in this talk, what about the spin magnetism in graphene? So the point is, when graphene is perturbed from the pristine system with many different approaches to produce or to induce magnetism. Currently, we know that there are different ways to induce magnetism in graphene. In this list, I present more or less historically appearing the magnetic properties in graphene. The first one of this system was the single vacancies in graphene. When we remove one carbon atom from the graphene lattice, a spin magnetic moment is induced. In fact, in this image, you can see the STM experiment confirming this prediction that the vacancy in graphene produce a spin moment in the lattice. After that, the second paradigm was the adsorbed impurities, and more recently, substitutional impurities. Also has been predicted and reported, experimental reported, magnetism at the edge of the graphene nanostructures. In this case, we have two types of systems. One of them is the graphene nanoribbons, mainly when we have the zigzag border, sorry. And the second one is when we have this kind of nanostructure that we call nanoflakes. So more recently also has been characterized the magnetism in polyaromatic hydrocarbons, very small structures, molecules, based also on hexagonal rings of carbon atoms. In this case, the magnetism is induced or resulting from the topological frustration and the sublattic imbalance. And very, very recently, we have the report of magnetism in graphene as a result of proximity. In this case, the graphene layer, a single layer of graphene, is on top of a mineral. This is an yttrium iron mineral, and the current in this layer is spin polarized. So as we can see, we have a very large menu of options to induce magnetism in the graphene. And this is a very important topic because, as we know, currently the production and the synthesis production and in fact the elaboration of devices based on graphene is possible. So there are a lot of interest to induce a spin polarized current in order to apply for application of graphene in the spintronic and other kind of new technology. So how we can explain currently this magnetism induced in graphene? The most common argument is based on the fact that graphene is a hexagonal lattice with two sublattices, triangular sublattices. Here are the green balls and the blue balls. And the green we call the A lattice and the B lattice. So the structure of graphene can be reproduced using these bases, these two carbon atoms, and producing all the hexagonal. As we know, the electronic structure, the chemical bond in graphene, is an sp2 bond in the plane, and a pi bond in the perpendicular direction to the graphene. So the argument to understand this magnetism in graphene is that when we remove one atom from this hexagonal lattice, we produce an imbalance in the pi electrons, in the pi bond or the p theta orbitals, and this unpaired electron, in order to reduce its energy, the spin is polarized. These kind of arguments are supported by general models like the Lie theorem. We remember that the Lie theorem comes from general modeling using a tie binding, Hubbard tie binding Hamiltonian, with no many details about the chemical bond, only using the pi bonds or the p theta electron in the model. So as I want to show you, this kind of argument is not sufficient to understand the magnetism in graphene. And to start, let me review some historical and interesting results about the magnetism inducing for a specific impurities in graphene. In this slide, we can see the main results from Yasser in 2007, predicting based on ab initio calculation. I remember that probably using the siesta code for hydrogen absorbed on graphene, and for the case of the vacancy, this is not vanadium, sorry, it's vacancy, the single vacancy in graphene. And here we can see the spin polarized maps, densities. And as one feature is that the main contribution to the spin magnetic moment is not exactly at the impurity side, is in the atoms, the first nearest neighbors atoms of the impurity side. And also it's interesting to note that the second nearest neighbors are polarized in the reverse direction with respect to the first nearest neighbors. So as we can see, the magnetism induced by hydrogen is not really simple. It's a complex process. In the case of the vacancy, the story is different. Here we have a dangling bond. This dangling bond, in order to reduce the energy, the spin is polarized. One interesting thing is that this work was published in 2007, and more or less 10 years after the experiment was realized by the group of González Herrero in Harvard, and they produced the graphene with a single hydrogen atom adsorbed on top of the graphene atom in the lattice. And using the STM technique, in particular the differential conductance spectra, they determine the density of states at the impurity side, and here is compared with the theory in the same paper. This was published in Science, and the agreement was almost perfect. So the impurity of hydrogen absorbed on graphene induced a spin polarization of the band structure. In the same report, they also study the magnetic moment using the same technique. The magnetic moment very far from the impurity. Here is the impurity, and they take this line and measure the spin polarized current, and they produce this kind of plot for the positive electron doping and hole doping. Here in this case, the doping I am referring to the current in the STM. So one important thing here is that as the theory predicts, the magnetic moment is not localized at the site of the defect, is localized around the defect, but mainly in the sublattice corresponding to the same sublattice where the impurity is absorbed. So the other interesting aspect is that this induced magnetic moment is very far from the impurity. As we can see here, we are talking about an nanometer scale. So we have induced magnetism very far from the impurity. Here we can start understanding that the magnetism in graphene, even that is produced by impurity, is not a localized magnetic moment. Other interesting system is the phosphorus. The case of phosphorus doping in graphene. This system has been studied from the theoretical point of view and reported in many papers, and in all of them, the people report a magnetic moment induced by the phosphorus. In this case, the impurity is substitutional. It's not absorbed. This is substitutional. And this impurity induces this kind of distortion in the graphene lattice. And in this report, very recently, more than 1 month ago, this group from Czech Republic produced the first samples of graphene doped with phosphorus, and they performed the characterization using atomic force microscope, and from that they determined the structural deformation in this situation, in this case. In the same report, they published ab initio calculation of the electronic structure, and in particular of the magnetic moment, and they predict a very sharp peak at the Fermi level, very, very sharp peak, producing a magnetic moment of 1 Bohr magnitude. So in summary, we have that in these two systems, hydrogen and phosphorus, hydrogen is an absorbent impurity and phosphorus is a substitutional impurity. The induced magnetism is 1 magneton, Bohr magneton, and also similar to hydrogen, the spin magnetic moment is spread around the impurity. Let me mention that in many of these theoretical reports are concluded about this magnetism, and they produce the very nice plots with the density of states and the magnetic moments, but there are not much discussion about the mechanism and in particular, what is the kind of magnetism that we are talking about in the graphene system. Let me remember very briefly how is produced the magnetic moment in the materials. In the case of the atoms, as we know, the Holmes rules explain why an atom has a atomic magnetic moment. In the case of solids or materials, we have two extreme cases. One of them is the localized magnetic moments, where the H atom in the system has a magnetic moment, and the other one is the itinerant magnetism, where the magnetic moment is localized in the atom, but also in the electron conduction electrons. The spin is polarized in the conduction electrons. Some systems corresponding to these extreme cases, for one side are the transition metal oxides. This kind of system, we can start to modeling these kind of systems using Hamiltonians like the Heisenberg Hamiltonians. And we know that this kind of system has a strong correlation, electron correlation. In the case of itinerant magnetism, the representative systems are transition metals, alloys, and also metals, elements with F electrons. D and F electrons are producing this kind of magnetism. So the question that we're trying to answer is, what is the kind of magnetism that we are looking at in graphene? Is from the experiments, it's clear that it's not a localized magnetic moment. Apparently, it's an itinerant magnetism. However, we need to characterize this kind of magnetism. Let me remember very briefly, the itinerant magnetism is based, conceptually is based on the Stoner model, where in the Stoner model, we assume that we have density of a state, a band, producing this density of a state for the spin up and the spin down. In the case of the paramagnetic system, we have the same number of spin up and spin down electrons at around the Fermi level. But in the case of the ferromagnetic system, we have that electron from the spin up, from the spin down, sorry, move for the band in the spin up and produce this spin imbalance. And finally, we have a magnetization, magnetic moment. One very useful criterion that is the successful result of this model is the Stoner criterion. The Stoner criterion established that the product of the density of a state at the Fermi level for the paramagnetic system times the Stoner parameter. The Stoner parameter is an interatomic properties related with the spin exchange, the strength of the spin exchange. And when this product is larger than 1, we have chance, or we have a magnetism. When this product is less than 1, the system prefers to stay in the paramagnetic configuration. So as we can see, in the case of graphene-induced magnetism induced by impurities in graphene, the people is talking that is related with the itinerant magnetism, and the idea of our project is to contribute to understand the magnetism properties, the character of the magnetism in graphene with SP impurity. For this end, we designed this study to analyze, to calculate properties using ab initio method for the substitutional impurities. And in the case of graphene, introducing atoms from the group 3 containing 1 electron less than carbon as boron, aluminum, and gallium, and also from the group 5 introducing nitrogen, phosphorus, and arsenic. The idea here is to see if the electron imbalance is the main reason for this magnetism. If these properties is symmetric with respect to the Hall or electron doping. To this end, we have performed ab initio calculation, as I mentioned before, using the quantum espresso code, here you can see some of the more important computational parameters. And very important to mention is that we study these impurities in the limit of less of 1% of concentration, in order to be sure that the impurity is isolated of the interaction between the other impurities. Another important thing is that that I want to mention is that in our calculation, we perform the magnetic properties calculations using the fixed spin moment, not the standard polarized method, in order to see what is the behavior of the energy as a function of the magnetic moment, because this kind of plot contain a very important information about the nature of the magnetism in the system. Let me remember that in the fixed spin moment method, in the initial calculation from the practical point of view, we fix the total spin magnetic moment, and we converge the charge, and we change after one value of the magnetic moment, we change the value, and we recalculate the system, the energy of the system, and relaxing the structure also. And in this case, we obtain a plot of the energy as a function of the magnetic moment. When the system prefers to stay in the paramagnetic state, the plot, the typical plot is like this one. The minimum is at the zero magnetic moment. But if the system has a paramagnetic instability or a standard instability, we can find that the energy has a minimum for a value of the magnetic moment different to zero. So this point, the minimum, corresponds to the equilibrium magnetic moment of this system. This kind of approach is very useful also to study magnetic phase transition as a function of a physical parameter, for example, the pressure or the strain, or even the doping. For example, in this cartoon, we are moving from a system, a magnetic system with a minimum in this point, and if the volume is reduced as a result of the pressure, applied pressure, the system shows a transition to a non-magnetic system. In this way, we can plot the magnetic moment as a function of the volume. We start from the equilibrium, and we are applying pressure, and eventually we have this kind of transition where the system is going from a ferromagnetic state to a paramagnetic state. This technique was introduced and used by Moruzzi many years ago, and produced very interesting results, contributed to understand the magnetic phase transition, mainly in transition method. Oh my God. Sorry. I played the ground. Okay, we're here. So, one slide more about a fixed spin moment. In general, we can find these three kinds of plots. This one corresponding to a paramagnetic system. This one corresponding to a spin polarized or ferromagnetic system, but with no saturation of the band. What means that? Means that some of the electrons in the spin down jump to the spin up channel, but one part remains in the spin up, in the spin down, and is producing this kind of plot. When the full band is polarized, the full band in the down channel is moving to the up, the electrons are moving to the up, we have this kind of plot. So please remember this this picture because we are using that to understand the kind of magnetism in graphene. To conclude about this slide, let me mention that this case is the paramagnetic, this case is the strong ferromagnetic case, and this one is the weak ferromagnetic case. Okay, now we are moving to presenting the results of these 6 systems that we have studied. In fact, we are included also silicon and germanium doped graphene. However, our expectation is that these systems are not magnetic, but we do that in order to be systematic. So we start from the group 3. We have a boron, aluminum, gallium. In red is the impurity band, the band induced by the impurity. At the 0 energy in all the plots is the Fermi level. Here we can see that the system is hole doped. This is the Dirac point, or the remembers of the Dirac point. And here is the Dirac point. This is pristine graphene. And this is the case of nitrogen, phosphorus, and arsenicum. And this is as you can see, electron doped system. But we call our attention about these 2 systems. We can see very flat bands introduced by the impurity, and a very large gap between these bands. So from the perspective of the Stoner model, these flat bands produce very sharp peaks in the density of state, contrasting with respect to the other systems where we have an important value of the density of state, but the peak is not so high and is not very sharp. From the point of view of the Stoner model, these 2 systems are expected to be magnetic, because remember that the density of a state at the Fermi level, if the value is high, we can change of inducing magnetism in this system. So here are the fixed spin magnetic moment calculation. As I mentioned before, we are plotting the energy as a function of the magnetic moment. And as our expectation from the last slide, the case of phosphorus and arsenico has lower energy when the system is polarized with a 1 Bohr magneton, and all the other systems are not magnetic. They prefer to stay in the paramagnetic one. Another feature that we learn about this plot is the behavior. As we can see, there are strong ferromagnetic systems. That means that the impurity band is full polarized. And one important point that we are trying to connect is this behavior of the magnetic properties with the structural properties. And here in this table are the values of the distance from the impurity to the first nearest neighbor carbon atom, the angle. This is the angle forming the impurity with the 2 carbon atoms. And this is the distance from the plane of the pristine graphene with respect to the system deformed after to introduce the impurity. As we can see, and as is expected for the small atoms like boron and nitrogen, the system is practically flat. There are no distortions. In particular, in the nitrogen case, is exactly sp2 bond. In the case of phosphorus and arsenico, we have a distortion, an important distortion. Also, in the other systems, however, remember that these systems like for aluminum and gallium are not magnetic. So here we have a first conclusion. Let me return to back. The atoms introducing a hole in the system are not inducing magnetism. The atoms introducing electrons induce magnetism. So the system is not really symmetric, as can be expected from the Lieb theorem. But one very strange case is the nitrogen, because nitrogen introduces one electron. However, this system is not magnetic. More later, I am coming back to this to understand this system. Okay. So in order to have more, a deep understanding of this kind of system, after that we saw that the kind of magnetism is the strong ferromagnetism or the full polarized band, we introduced this. We use this model. This model is based on the ideas reported before by Michael Carneson and also Peter Mon, and we adapt the model that they suggest to explain the magnetism in this kind of system to a narrow band ferromagnetism. The elements are this one. We assume a rectangular band density of a state for the two spin channels characterized by this bandwidth, and we calculate analytically the chain of the energy as producing as a result of the spin polarizing. In this case, the density of states for the systems at the Fermi level are these values. And here theta represents the magnetization, and the number of electrons, and m the magnetization. This is the difference of the number of electrons spin up minus spin down. So after to work with this model, we obtain this expression for the energy as a function of the magnetic moment is a quadratic relation between the magnetic moment and the energy, and the two K parameters are the width of the impurity band and the electron repulsion or Coulomb repulsion of the electrons in the band. As we can see here, if this term is positive, the system is not magnetic. But if this term is negative, we have magnetism. So from that, we obtain that the condition similar to the Stone criterion to obtain magnetism is that the ratio between the electron repulsion and the bandwidth is larger than 1. We have magnetism. So fitting this expression to the calculated fixed spin moment, we obtain the electron repulsion because the bandwidth is obtained directly to the band instruction. In this table, we summarize the results for these systems, and as we can see, as we can saw in the band structure plots, the phosphorus and arsenicon are the smaller bandwidth, and these two systems fulfill the criterion and are magnetic. These barriers are resulting from the ab initio calculation, and this criterion is from this simple model. Another interesting thing is that in all the systems, the electron repulsion in the band is more or less similar, about the 200 milli-electron volts, more or less. So as we can see, the K parameter controlling the magnetism in this system is the width of the impurity band. So now, okay.
Sorry to
so now let me show the spin polarized band structure for phosphorus in graphene and arsenicon. Here we can the spin splitting band. This is the spin density in the real space. But in order to see more in deep this plot, let me show this analysis. This corresponds to the phosphorus in graphene. As we can see, in red are in red are the spin up, in blue are the spin down. As we can see, the spin distribution is spread on all the lattice. These points correspond to the impurities. Okay. And after, in order to be more quantitative, we take a circle around the impurity, and we take the number of electrons in the pi bond and the sigma bond is this plot. These numbers are phosphorus. This is carbon. The first number is the order of the nearest neighbor. This is the first nearest neighbor. This is the second nearest neighbor, and so on. And the second number is the number of nearest neighbors in this chart. So one interesting point is that the larger part of the spin magnetic moment is in the pi bond. However, the sigma bond also is contributing. The other point is that not all the system is ferromagnetic in the sense that all the atoms are in the same direction of the magnetic moment. Some of them are spin up, another one is spin down. So another interesting thing is that the largest part of the magnetic moment is not at the impurity site, as was reported before, is spread on all the lattice. Let me go back to the case of nitrogen. Remember that nitrogen has 1 electron more than carbon. However, it's not magnetic. As we saw in the structural parameter results, this system is completely flat, is in the sp2 bond. And so in order to see how the distortion is playing a role in reducing magnetism, artificially we introduce a bonding transition from sp2 to sp3 in the case of nitrogen. What means that? We means that artificially we pull up the nitrogen atom, and we calculate the electronic band structure and the magnetic moment for as a function of this distance, the distance between the nitrogen atom and the plane of the graphene. In this plot, we can see the impurity bandwidth as a function of this distance. Remember that in the equilibrium, nitrogen is in the plane, sorry, it's completely flat. And as we pull up, the bandwidth is reducing. And in this point, we change from sp2 to sp3. And very interestingly is that the magnetic moment is exactly jumping to a value different to 0 after to reach the sp3 bond. That means that the systems, even if the system has 1 electron more than the atom, the impurity atom has 1 electron more than carbon, is not sufficiently conditioned to induce magnetism in graphene. We need, in addition, that this sp3 character in the chemical bond exactly at the site of the structure. And continuing with the distortion, we can see that we reach the value of 1. That means that here the band is full polarized. But if we continue producing this distortion, the magnetic moment is reducing from this high value, from this top value, because the bandwidth is going up again. So that means that the width of the impurity band is the key parameter controlling the magnetic moment in this kind of system. So we have more results about this kind of system. However, because the time was finished, I stop here, and and let me summarize our conclusion. So from the analysis of the present results, we can say that the electron imbalance in this kind of impurity systems is not sufficiently to explain the magnetism in the case of SP impurities in graphene. Even more, we find that the K parameter controlling the magnetism is the width of the impurity band, and which at the same time is depending of the hybridization degree, and we have magnetism when this distortion is around or is after to the sp3 chemical bond. Many thanks for your attention.